So let's determine the pH of a solution that has an OH concentration of 10 to the negative 9. All right, so now when we're doing this, can anybody predict what the answer is before we do this problem? So what do you think this is before we do the problem? And you feel free to like say it out loud, or you can type it in the chat. What do you think? I'm seeing a few. So what do you think the pH is? So using our knowledge of pH. So when I look at this, I think a pH is 5. So now again, if you can't do this yet, it's okay, but we want to develop the skill because it's going to make our lives a lot easier later. So when we do this, we have OH and we can do pH or POH. So I'm just going to do pH regular for right now. So let's see here if I can do this. Yes, you can see this now. Okay, so when we do this, we're going to find our H3O plus concentration by using KW. Remember, KW is just H times OH equals 10 to the negative 14th. Then we're going to solve for our H3O plus, and then we'll get our pH. Now, again, you could do this doing POH, which we'll talk about in a second, or you can do it the long way. So remember, when it says pH, it means you need to talk about the hydrogen ion concentration, and that's going to become very important. Right now, you're like, yeah, obviously. It's going to become very important in a little bit. Okay, so we used our KW, which we did last week, easy peasy. And then we found out our H3O plus concentration, took the negative log of that, 5.40, right? And so in my brain, right, what I did was I saw this was 10 to the negative 9th. If this is 10 to the negative 9th, that means that H is probably around 10 to the negative 5th. If H is about around 10 to the negative 5th, the negative log of 10 to the negative 5th is 5. And that was my predicted pH. Now remember again, just real quick with our sig figs, 2 sig figs here, 2 sig figs after the decimal, right? Okay. Now, what about if we want to determine the OH concentration if we're given the pH? So this is a different formula, not hard, right? Remember, if you want to get rid of the log of something, you take the anti-log, which in your calculators is the 10 to the X button, right? So here's the formula that you need to know. And it's just so 10 to the negative pH. That's how you get rid of that negative log. So you take 10 to the negative pH. And so remember, when we take the 10 to the negative pH of this, that's going to give us our H3O plus concentration. We want OH, right? So we need to make sure that we convert this to OH, because if this was a multiple choice question, I'm just going to do this first part here. Oh, look, I don't have it on here, so I'll just write this. If this was a multiple choice question, we have 10 to the negative 5.4, which is, I don't have this on here. Hold on. Trying to write this neatly. .98 times 10 to the negative 6. But again, this is H. We don't want H. We want OH, right? So we just take 10 to the negative 14th and divide it. Now, another way you could do it is using POH. So if you did with POH, you would just take 14 minus this. And then take 10 to the negative of it. So 10 raised to the negative. I just think this way is faster. 10 to the negative. And you get, shoot, mine's graphing. Sorry, I stole this computer from my office mate. So we have H plus times OH minus. I'm going to do it the long way and the short way. 1 times 10 to the negative 14th. If our H is 3.98 times 10 to the negative 6 equals OH, or multiplied by OH equals 1 times 10 to the negative 14th. Divide this. You can do this faster than me. Type the answer in the chat. And I'm seeing a bunch of them. Yes. So we end up with 2.51 times 10 to the negative 9th. Remember, that is our OH, right? Yes? Okay. So now, how would we do this the other way? Let's just go back. This should work when I go back. We'll see. Does it work? Do we get 2.5 times 10 to the negative 9? Ah, see, look, 2.5 times 10 to the negative 9th, right? Which is exactly what we started with. We just went backwards. Let's put this on here. We just went backwards from our last problem. And again, you can do this a different way. So let me show you the different way I keep talking about, and I'm assuming most of you remember it, but just in case. So POH. So POH, remember, P just means negative log of whatever's behind it. So POH means negative log of OH. So you can use POH like this, or you can use POH like this, just like you're using hydrogen. You just remember that we're talking about hydroxide instead of hydrogen. Whichever way you want to use, and we talked about this a little bit at the end, whichever way you want to use to solve pH or POH when we're doing acids and bases is fine with me. So just whichever way your brain works, if you want to use KW or if you want to use POH, that's fine. This is kind of like our little thing, pH plus POH equals 14. So that's why in the last problem, we had 5.4. So this is 5.4, right? So if I just took 14 minus 5.4, that's going to give me my POH, right? And then I can just take 10 to the negative whatever that is, right? 10 to the negative whatever that is, and that's going to give you my OH. You end up with the exact same answer. So this is 8.6, and then 10 to the negative 8.6. Sorry, it's supposed to be an 8. Will give you 2.5 times 10 to the negative 9th. Whichever one you want to use, fine with me. Okay, so this is how we get that, and we actually talked about this last time, so I'm just going to go right through this slide because we talked about how we got POH plus pH equals 14. If you want to look at this in greater detail, you can. I'm never going to ask you to prove it, though. Okay, so let's try this, and again, you can do this any way you want. So calculate the pH at 25 when the OH concentration is 1.3 times 10 to the negative 2. So we want pH, but they gave us OH. So we could use KW, and from KW, we could get to the hydrogen concentration, and then we could just take negative log of that, or we could just use POH, which we've already talked about. Well, that's kind of a lot faster. So if we just take the negative log of our OH, that's going to give our POH, and then we just subtract from 14. So it's much faster. So we, again, negative log of what they gave us is our POH. So now we just need to take this 14 minus this, and that's going to give us our pH. Now, when looking at this, if my OH is negative 2, I'm guessing my pH is around 12, right? So you should be getting a little bit better at being able to kind of go back and forth like that. Okay. Now, what if we want to do the opposite? So if we look at this one, we want the POH, and our solution of H2O is 10 to the negative 9, right? So let's see if anybody can do this in their heads backwards. What do you think the POH is? See if you can just look at this and try and guess what do you think it is. Any guesses here? No? Okay, so here's the thinking in my mind. If this is negative 9, remember they always add to negative 14. That means that H must be about 10 to the negative 5, right? All right, OH must be about 10 to the negative 5. POH meaning it should be right around 5, right? So this is my guess. Shall we see if I'm correct? And again, you could use KW with this, but POH is just a little bit faster. And these problems, I'm assuming that we're all pretty good with these. And so if we do, oops, let's try it. So let's try this one really quick. So if we have, determine the POH, the H3O plus, so we could take negative, sorry, every time I touch it, it moves. Negative log of 2.5 times 10 to the negative 9th. That's going to give us our pH, right? Which is 8.6. This is our pH, but they asked for POH. So we take 14 minus 8.6. I can put things in my calculator correctly. You should get about 5. Yeah, 5.4. My sig figs are one off, but that's okay. And this is our POH. Okay, so that's kind of where your quiz ends up at doing these things. So there's gonna be a lot of practice on Chem 101, which I know a lot of you have already finished, but that's kind of what your quiz is for this week. Now we're gonna kind of start on, now that we have the basis of those, we're gonna be using these pieces right here. They're gonna end up being like the very end of what we're doing later. So first we're gonna learn about pK. Now remember what I said about P. P, negative log of whatever's after it. So pK means negative log of K, right? And so in this case, we're talking about acids and bases. So pKa, negative log of the Ka. Again, K is K is K. We just put an A after it because it's an acid. Kb, again, K is K is K. We just say B because we're talking about a base, right? And this is a nice little thing to remember. Now, sometimes you will actually get really good at doing this a little bit later, but right now we just need to remember that the stronger the acid is, the smaller the pKa. So if you're going to compare pKa's, because it's negative log, it's not the stronger the acid, the higher the pKa. The stronger the acid is, the smaller the pKa is. Same thing with bases. Again, it's because of negative log. You're welcome to put in Ka's into your calculator to prove this, but the stronger the base is, the smaller the pKb is. So remember that. So it's kind of the opposite in your brain because again, it's that negative in the log that flips it. And we're gonna be using pKs a lot. But remember, P, negative log of whatever is after it. Okay, so now we're gonna talk about strength of acids and bases because we're gonna do mixtures in just a few minutes. So there's two sources of hydronium in an acid, right? There's the hydrogen ion concentration from the acid, and there's the hydrogen ion concentration from the water. Remember, water at 25 degrees is 10 to the negative 7th molar, right? Same thing with the base. If you have a base, there's the hydroxide concentration from the base and from the water. And again, at 25 degrees Celsius, that's 10 to the negative 7th. Now, if you have a strong acid or a strong base, you can ignore the contribution of the hydroxide or the hydronium from water because it's so tiny, right? It's like 10 to the negative, right? It's 10 to the negative 7th molar. That's very small. That's a very small concentration. So except for if you have a super, super, super dilute amount, right? And we're talking dilute like 10 to the negative 4th molar because you can see this is kind of close, right? So if you have a really, really, really dilute strong acid or strong base, then you might need to think and take a look at the Kw from water because it could contribute to it. But for the most part, if you have a strong acid or a strong base, you don't have to worry about it. Okay. Now, finding the pH of a strong acid, strong acid or a strong base, finding that pH of a strong acid, super easy. Negative log of the hydrogen ion concentration, right? We've just done that one. And remember, acids ionize one hydrogen at a time, right? So when H2SO4 ionizes, it goes to H plus H SO4 minus. And then this can continue to ionize again to H plus and SO4 2 minus. Acids ionize one hydrogen at a time. It's a one hydrogen at a time. Bases are different. For bases, I'll use calcium hydroxide. When this one, Ca2 plus 2O minus, 2H minuses. This is not stepwise. Both of the hydroxides come off at the exact same time. And so therefore you need to take into account the number of hydroxides when you're doing the pH of a strong base. Okay, on your exam number 1, the most common missed question is me asking the pH of a strong base. Now, your exam 1 is really hard with really, really hard questions, but the most common missed question is this. When I ask you the pH of a strong base, when you have the pH of a strong base, you have to take into account the fact that if you have a 1 molar concentration, when that comes apart, 0.1 molar of this, you have 0.2 molar of this, right? So we'll do a few practicing with that. If I can get my, okay. So now, first, let's look at the pH of a weak acid before we do this. So if we have a strong acids are strong electrolytes, meaning they come apart completely, right? But weak acids don't come apart completely. And so for a weak acid, we have this, and this goes into our equilibrium expression, right? Because we can't just say we have this, there's only a little bit of this, but lots of this. So guess what? Looks like an ice table. It is an ice table. But this is an ice table you've solved many, many times, right? So for example, if we want the pH of a 0.2 molar solution. Now, one of the most important things over the next month that you need to be able to do is you need to be able to write the equations. Understanding the Bronsted-Lowry idea of conjugate acids and conjugate bases is going to be your best friend, right? So you need to know when I put HNO2 in water, what does it make, right? So this is an acid. Acids lose hydrogens. So this is going to become NO2 minus, this must be the base, it's going to gain hydrogens. Skipping this step and just going straight to the ice tables and straight to the math might seem like a great idea now. It's a very bad idea next chapter, right? So just get used to, and right now on your notes, I give you these equations sometimes, but you really need to get used to being able to write these equations and understanding. And being able to write these equations, the fundamental understanding is the Bronsted-Lowry acids and bases. Okay, so now, here's our equation. This is what's going to tell us what goes in our ice table, right? So here's our ice table. Again, we're not going to put water in there, but we're going to have our acid, our conjugate, and our other conjugate. Now we're going to start with 0.2 of our NO2, right? And when we do that, we're also going to need our Ka. We know that this can only go forwards, right? So this has to go down, and this has to go up, and this has to go up, right? That's something we definitely know that has to happen, right, when we're doing this. And so when we do this, this is going to go, yeah, I'm just going to go to this slide. So this has to go down, this has to go up, this has to go up. When we have our equation, which I have down here, they're all ones. Well, this doesn't matter. Ones, right? So it's going to be minus x plus x plus x. And it's going to be, again, 0.2 minus x, x, x. Now, our K, I had it on the last slide, which, let me see if it pops up here. It was like 4.6 times 10 to the, I can't remember. 4.6 times 10 to the negative fourth is our K. So when we do this, our K, remember, is going to be our products, NO2 minus, times H3O plus, over HNO2. Minus x plus x, 0.2 minus x plus x, or not plus, just x. So when we put this in, we have our Ka equals x squared over 0.2 minus x, right? So this is what we end up, and this is our Ka. And remember, our Ka was like 1.4 times 10 to the negative something. So now we're just going to plug in our numbers. But remember how our x is small? We're going to use our x is small. And when we do our x is small, here this is neater. So we're going to do our x is small. When we do that, we're going to ignore this, right? But remember, when we decide x is small, we need to check, right? We need to check. And what we're doing is we're going to check and see if the change in our original concentration is less than 5%. So if this difference is less than 5%, then we can use our x is small approximation. So now I'm going to plug in my K. Here's our K. By the way, if you're doing this on Chem 101 and you're like, they're not giving me a K, usually there's a table you can click on, or I just Google what is the K, whether the Ka for whatever we're doing. Okay, so ignore our X. Now we've got a super easy problem to solve, right? Multiply by 0.2, multiply by 0.2, take the square root. And we get 9.6 times 10 to the negative 3. Now, that means that our H3O plus concentration is 9.6 times 10 to the negative 3, right? And they want the pH. So now all we need to do is take the negative log of that. But first, before we do that, we need to check and see if our x is small approximation was indeed correct. So let's check. So remember, when we do x is small, here's our change, right? So that was our 0.2 minus, this was supposed to be our 0.2 minus x. The question is we need to check it against what we started with, right? So when we do that, and now let me see, where are we here? So we have, it's going to be tight. If this one works, it's going to be tight. So we have our x, that's our change over our original concentration. Less than 5, but just barely, right? That means that we don't need to go back and solve the math in a more difficult way. We can do it using the simplified manner because our x, again, was less than 5%. So now we can find our pH.
Go back to the other slide.
This one?
Yeah.
Not a problem. So a nice little thing to note here on this one, again, this 9.6 times 10 to the negative 3, that's our change, right? So that's the change in the initial concentration, right? So we want to know, if we want to know how much this initial concentration changed, when we divide this by this to get our 5%, that's the amount it changed. Now let's look at this reaction really quick again. HNO2 plus water goes to NO2 minus plus H3O plus. So when we divide those two, we got 4.8%. That means that 4.8% of this went to products, right? Because that's how much of it went from reactants to products. So 4.8%, we say ionized, became ions. So our x is small actually has two purposes when we're doing our acids and our bases. And we'll talk more about that in just a minute. So it ionized 4.8%. So that's what we call the percent ionization. But again, we still have to find the pH. It's just the negative log of our x is our pH. So I found out these other concentrations, but you don't really need these, right? We just need this piece. I'll show you, the reason I find these here is so we can check to see if our answer is correct. Remember, the thing with ice tables is you can kind of always see if your answer is correct because you can put in your equilibrium concentrations and you should get the original K you start with, right? So Even though I don't need this, I still found this. This is the number I need. So we just need to take the negative log of that, and then we will have our pH. So I put in our new equilibrium concentrations, and our pH is 2.0. Oops. 2.02. But I have the sig figs wrong. Here's the correct sig figs, right? Because this is 0.200. So because that's 3 sig figs there, 3 sig figs past our decimal place. So this is very similar to the ice tables we did. There's just a couple little more steps here, right? So questions on this. Do you want me to go back? Anybody have questions on any of these pieces? Okay, so I'm just going to check real quick. I'm just going to put these numbers into the equilibrium expression, see if I get this. Just real fast. Aha! I did get that, right? Now I know people are like, oh, I don't want to. This just takes too much time. I don't want to do that. I'm telling you, just do it. Just do the check. That's how you know if your answers are right or not, right? So I would definitely check, especially right now where you're beginning on this. Okay, you ready for another one? Yes. And again, it doesn't have to be exact, just close, right? There's a lot of sig figs going on here. Okay. Let's try another one. What is the pH of a 0.012 molar solution of nicotinic acid? Now, remember, if it's a strong acid, all we have to do is take negative log of it and we're done. But if it's a weak acid, because it only partially ionizes, we have to do an ice table. Now, how do you know the strong and weak acids? Memorize the strong. That's how you know. Everything else is weak. So this means this is a weak acid. So the first thing we do is we have to write the equation. And again, don't shortchange yourself and skip this piece. It is going to be so important in next chapter, so important. So when you do this, if this is an acid, and we're putting it in water, right? Acids donate hydrogens. So this must be the conjugate. So if this is the acid, this is the conjugate base. That makes this the base. Base is gain. This is the conjugate acid, right? This is an incredibly important part because when you write your ice table, you need to know what you're putting in. Like so many times people are like, I don't know what I'm putting in. This is what you're putting in. So if this is your reaction, R for reaction, here's this, HC6H4NO2. Here's our next piece, C6H4NO2 minus. Here's our next piece, H3O plus. When people don't get ice tables wrong, it's almost always because they don't know how to set them up, right? So don't sell yourself short. Set up the ice tables using the reaction. So when we do this, right, it says we have 0.012 of this. Means we don't have any of this, and we pretty much have none of this. Like, so I've gotten the question before, like, oh, isn't there 1 times 10 to the negative 7th molar? I mean, yeah, but this is -2. Negative 7th, the difference in the decimal is so far down. The difference is going to be at 0.00000, like 5 places past where we're measuring. And we're not going to see the difference. So we just negate the effect of Kw, the hydrogen ion concentration from Kw, because it's so small. So we just say it's 0. So this has to go forwards because there's no products. So this has to go forwards, right? That means that this has to go down. This has to go up. This has to go up. They're all 1s. It's a really nice thing about acids. They always lose one hydrogen, so they're always ones. Love that part. So this is going to be 0.012 minus x, x. So we put this in here. We have our K. And again, I'm just going to put an A here because it's an acid. But really, you're not treating it any different than you did last. This is like the same problem that you did before. Exactly the same as chapter 14. The only difference here is there's one more step because we have to do the pH at the end, and we have to write the reaction in the beginning. So I'm not going to write the whole equilibrium expression. I'm just going to do like this, x squared over, I don't want to write any more nicotinic acid. I'm going to say that's small. So then my equation is just Ka equals x squared over 0.012. Now you can see I need my K. So I don't have my K on this one. So I'm going to have to go to my next one to find my K. So I'm going to give you a second to write down what you have because I'm going to go to the next one in just a second. Everyone good here? Trying not to go too fast. I can always go back. So here's where we were. We assume x is small. Ah, there's my Ka. So then I'm just going to plug in my Ka. Right, and we solve for x. Right, multiply by 1.2 times 10 to the negative 2. And then take the square root. And we get 4.104. Now, remember, this is our x, or our change. Before we can go on, we need to check and see if it's less than a 5% difference. Ooh, -5, -2. Maybe. It's going to be close. Maybe. So again, we're going to take this over our original concentration to see if the change was less than 5%. So remember, what this is saying is this 3.4%. It's saying that this decreased by 3.4%. That's what it's saying. So it means 3.4% of it went over here to products and ionized, right? Ionized means made ions. So our approximation is valid. So now all we need to do is take negative log of 4.1 times 10 to the negative 4. And that is 3.387. Is our pH. So a couple of things. We know this is an acid because it says it's an acid. So your answer needs to be less than 7. Specifically, your answer needs to be between 0 and 7, right? So if you get an answer and you're like 49, no, right? Or you get a negative answer, no, it's an acid. Your answer is between 0 and 7. Right? So you kind of know where your answer should be. So if you get some kind of a weird answer, you know something's wrong. So that's why I always suggest going back and checking it. And so in order to check it, all we're going to do is I'm going to put in our x here, here, and here and see what you get. Look, when I subtracted 4.1 times 10 to the negative 4 here, it didn't even change this number. Right? The difference was so small, it didn't even change the concentration. So some of it ionized, but the amount that ionized was so small, it was negligible, which is exactly what we proved with our math. So I'm going to use these in a minute to check my answer. So pH 3.38. I think we decided this is wrong with the sig figs, right? We need one more sig fig just because of this has 3 and this only has 2, but close enough for now. So we got our pH, and then we're going to check it. Again, the reason we check it is we know our answer is correct. If we put all of these equilibrium numbers into our equilibrium expression, and we get a number, that matches what we started with, or that's really close. Then you know there's a very, 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 very high chance, 99.9% chance that you've done the problem correctly, right? Okay, questions on this one, because now I'm going to have you do your own. Questions? Okay, this one's for you. I'm going to have you try this one. Let me get you the Ka. Just really quickly. The Ka to HClO2. It's 1.1 times 10 to the negative 2. Okay, I want you to try this one. Go as far as you can. Some of you will already be able to completely do this on your own. Some of you will be like, I can't write my equation right. It's okay. Try this. See how far you get, and we're going to go over it in just a minute. Okay. So I see a few people have gotten through it. So let's, step 1, write the equation. Remember, we said that this is an acid. If this is an acid, this is a base. This here, this is what's on your quiz this week, right? If this is an acid, acids lose hydrogens. This is its conjugate base. Bases gain, right? Again, this is what your quiz is this week, right? So that little piece is on your quiz this week. Now, this tells us how our ice table is to be made, right? So here's our ice table. So here's, I made this very big. So our first part is HClO2. Our second part, ClO2 minus. Our third part is H3O plus. Initially, we have 0.1. I'm just gonna put 0.1. I'll worry about my sig figs later. 0.1 of that, none of this, pretty much none of that. The change is this is gonna be 0.1 minus X plus X plus X. Well, let me just do minus X here. At equilibrium, 0.1 minus X plus X plus X. This is last week's quiz, right? And then I gave you your Ka. So your Ka, which I'm just gonna do it with the, I'll do it from the beginning. So Ka equals products over reactants. Then we put our numbers in. 1.1 times 10 to the negative 2 equals X times X over 0.1 minus X. Or X minus 0.1. I should do that. Doesn't matter because we're going to ignore it anyway. Okay, so now I'm just going to do this all neater. Here's everything we have. Oops. So this is where we got to. Okay. 0.1 minus X. And then we're going to be like, ignore that. Right? So now we're going to ignore that X. And we're just going to end up with X squared over 0.1. Right? So we're going to super simplify our math because we're going to assume that this change in X is very small. So again, I got rid of my X. Here's my K. So solving it is like wonderful and lovely. Now, again, this whole piece, this was last week's quiz, right? This is last week's quiz. Now, we're going to go to this week's quiz again. So if our answer is X is 3.3 times 10 to the negative 2, that is our H3O plus concentration. So we just need to take the negative log of that. So the negative log of 3.3 times 10 to the negative 2, that's our pH. I got 1 point, looking for my sig figs here, 481 for my pH. Let's see if we got close enough on this. Okay, so I'm going to walk you through all this math again. Oh yeah, that's right. So this is our pH we decided, right? 1.481. But what did I forget? X is small. We forgot to check if X is small, right? Now, if we look at this one, I want you to notice something. This is 10 to the negative 2. This is 10 to the negative 1. Remember what I said last week about if X is small will work? The difference in your exponents needs to be about 0.3. You're safe at 0.3. This difference is only 0.1, so our X is small isn't going to work. That means we can't use this as our pH. Now, we can prove that our X is small isn't going to work. We just check. We're going to take this number here, divide it by this number. Now, a lot of times people are like, I know which number divided by what number? You take your X, the answer you get, and you divide it by the original concentration. It ends up being the top left box every single time, right? So it's your X divided by the top left box. Because what we're trying to see is we're trying to see when we subtract this amount, is this number going to change more than 5%? Well, since this is a negative 2 and that's a negative 1 exponent, it's definitely going to change more than 5%. Like for definitely going to change more than 5%. Right? So if we do this, we have 3.3 times 10 to the negative 2 divided by our original 0.1 times 100. And we get, 33%. Yeah, X is small doesn't work. So therefore, there's two options now. We can either do successive approximations, or we can just do a quadratic formula. Really, at this point, it's completely your choice if you want to do successive approximations or if you want to do the quadratic formula. Both of them work. I think I solved this one using quadratic. I did, yes. Okay, so that means we can't do this on this problem. We can't, it doesn't work. So if we do it using quadratic, right, we have this becomes x squared, right? And then we're gonna multiply each side by this. And we end up with this being our equation. We multiply this through, right? And again, this algebra is a little long. I'm not going to take the time to do this algebra. If you have questions on it, we can go over it. And then remember, x is small. Quadratic formula, right? Negative b, right? Minus 4ac, b squared, that whole thing. Now, we have two choices. Only one of these makes sense. So how do you know which one makes sense? So I'm going to go back. I promise I'll come back to this math in just a second. We're looking here at 0.1 minus x, right? Only one of these can be x. So it's either 0.1 minus 0.028, or it's 0.1 minus negative 0.039. This, right, minus a negative, this would mean it would increase. No, it can't go up, it has to go down, right? I promise, I will come right back here. Right, this has to go down, these go up, right? We're only starting with reactants here. That's all we have is reactants. They can't go up, they can only go down, right? So when you do a quadratic formula, only one of them is going to make sense. Right, only one is going to make sense. The other one's not going to make any sense. Avanish, did you have a question?
Yeah, the x can never be negative if one of the products is x, right? Because you can't have like a negative concentration. So that would be like just the easier way to find out which one is the x you need to use.
Yeah, well, this is and x can never be negative. Yeah, you can't have a negative H3O plus concentration. Absolutely, that's another way to look at it too, right? You can't have a negative P. You can't have a negative H3O plus concentration. Yes, that's a good way to think of it. Okay, so now if you did successive approximations, your answer should be very close to this. It might not be exact, but in the end, it will be close enough, right? It'll be close enough. So when we do this, we got our x was 0.028. So that means we're going to have 0.1 minus 0.028. This is going to be 0.028. And this is going to be 0.028, right? So if we plug all those in, here's our change, right? So this equals 0.072. Now again, we don't necessarily, need all of these, but they're good to check in the end, right? This is really the one we care about. Now we just need the negative log of this, and we should be good. So let's look at how close we were to our answer. So before, with our x is small not working, we got 1.481. Now, you can see with the correct x is small, with the correct without using x is small, we got 1.55. And then if we want, we can check it. So this is this week's quiz, this piece, right? So this week's quiz has the equations, Bronsted-Lowry, the pH, but not the middle part with the ice table. Next week, we're going to put them all together. We're going to have the whole thing together. Okay. And then if we check, we get 1.12. Shoot, I erased the other numbers. If you did this with the x is small, and let's say you forgot to check x is small, you don't get 1.1 times 10 to the negative 2. It's kind of far off. We don't have time to do it right now, but you can see it's kind of far off. It doesn't match. It doesn't match well. And so that's kind of like our way of going, oh gosh, like that didn't work quite right. Okay, so now, oh, Avnish did it. He got, so 1 point, so Avnish actually did this for us. So when we did not do the x, when we assumed the x is small was correct, we didn't check, you end up with your k equaling this. Look at how far off these are, right? Really far off. So that's why I say always check to see if you end up with the same k in the end, because it will tell you if you've done something wrong, because it works every single time, right? Your k should match. Now again, not exactly, but it definitely shouldn't be off by a factor of 10, right? It may be off in a few like tiny significant figures, like just a tiny bit, not a lot. Okay, let's try another one of these. So when you first see these, they seem like they're kind of crazy. Now this one's a little bit different. So let's look at this problem here. What is the Ka of a weak acid? Okay, so now this time they're asking us for K. They're giving us a concentration and a pH. So if we want to find K, all right, so first of all, we don't even know what this acid is. It's just a weak acid. So I'm going to write the kind of generic acid. So HA means acid. We're going to put the acid in water. Acids lose hydrogens. Bases gain hydrogens. This is this week's quiz right here, right? That's a this week's quiz. This is the generic form. And you should get kind of comfortable with this generic form. I know it's weird, right? So this is what we've got. And we want to know the Ka of this acid. Okay, well, K is going to be products over reactants. Okay, well, we've got some things here, right? So this pH, the question is, what is this pH? So this is the end, right? They're telling us the pH in the end. So at equilibrium, we can find the concentration of our hydrogen ions because that's what the pH is, right? So if I go back here, just so you see, our ending answer was the pH. We use this number right here to find the pH. The problem I'm showing you right now, they're giving us this number. So we can use this pH and find our equilibrium concentration of H3O+. So they're giving us a piece of the ice table, right? So in the equation that we have here, they're giving us a piece of the ice table, right? So we have our HA minus H3O+. They're saying, hey, this is how much HA you have, but hey, this is your answer right here. So we can use this to figure out the X's. I mean this here. Because that's going to be our X, right? Which is going to give us this X, which is then going to let us figure out 0.1. Right? It's giving us our X, right? So this is actually an easier problem because we don't have to do all the math. Okay, so how do we get our hydrogen ion concentration? Remember, 10 to the negative pH. This is a piece. This is what's on our quiz this week. This piece right here. If they give us pH, you just take 10 to the negative pH, and that is our hydrogen ion concentration, right? This is H plus at equilibrium. So we have our ice table. Here's the concentration they gave us, but we have one of the answers. Well, that's nice because now we can find our change. If we can find our change, then we can just plug it in and calculate our K. And again, this has to go forwards because all we have are reactants. So this has to go down, this has to go up, this has to go up, right? And the amount it's going to go up, it's right there. Right? So they're telling us how far it's going to go up. So this is going to go up by 5.6 times 10 to the negative 5. This is going to go up by 5.6. See if I can write that a little neater. This is going to go down. So our change would be 0.1 minus 5.6 times 10 to the negative 5. And this is just going to be this. So now we just need to plug it into our K, right? K equals A minus times H3O plus over HA, right? And we're going to plug these numbers in here. So I'm just on the next page, I have this much nicer. Here it is. See, much nicer. So now look at what happens, by the way, when you do this. When you take 0.1 minus 5.6 times 10 to the negative 5, and you actually put this in, it doesn't change it at all, right? That's an X is small kind of thing. Doesn't change it at all. It changes it. Never mind. It does change it. Let me show you where you change this so I can clarify when I say it doesn't change it. That's what you get. But when we use our sig figs, it rounds to point, right? So it changes it. It does change it. I don't want to, when I say it doesn't change it, it does change it. But the change is so small, we can't see it in our calculations. It's beyond our significant figure mark. So it still does change. It just changes the tiniest bit where we ignore it. Okay, then we plug all this in and we get, so there is our K. So it's still using ice tables, but it's not, it's got a little twist on it, right? They gave us this answer here, which makes our math easier, less or no algebra, which is nice. Okay, let's try another one. Okay, this is the same kind of problem we just did. I'm gonna have you try this one. Very similar. This time you're gonna find the Ka. I gave you the acid, but you don't need it. Don't look at the Ka, you already know the answer because we've done it. I want you to try doing exactly what we just did and see if you can get the same answer. So same type of problem, try this now, and then we'll go over it in like 3 or 4 minutes. Okay, I'm seeing a bunch of these come through now, and they're very close to each other. So again, the first thing we're going to do is find our hydrogen or hydronium concentration. Again, this is like your quiz that's from this week, as this is, right? It's writing our equations and understanding our conjugates. Then we're going to put it into our ice table. Here is our change. So when we put in our changes, we can see now when we subtract 0.4 times 10 to the negative fourth from 0.0012, it's going to be beyond our significant figures. So when we do this, we end up with the same exact thing. We end up with 1.3 times 10 to the negative 5. Okay, so it should be about and around this. And I get sig fig questions on this. So this is 2 sig fig questions because it's from pH. So the sig figs backwards is the same thing forwards. So this is only 2 sig figs. Now, if it's on a test and you gave me 3 sig figs, I wouldn't count it wrong. It's within 1. We're okay within 1. Okay, so now we're going to talk about polyprotic acids. Polyprotic acids are like sulfuric acid, phosphoric acid, acids that have more than 1 H. Now, remember, when they ionize, 1 H at a time comes off, right? So a monoprotic acid, that's like HCl. Diprotic acid, H2SO4. Triprotic acid, H3PO4, right? It's just a number of protons. And remember, the hydrogens come off 1 at a time, right? So every time we remove a hydrogen, the second hydrogen is harder to remove, right? It's harder to remove. So every time we remove a hydrogen, the polyatomic ion holds on to the other hydrogen even harder. The harder it holds on to it, the harder it is to pull apart, which means that it's going to be very difficult to get it to ionize, right? So, for example, and we're going to talk about this in great detail. This sulfate and this hydrogen are attracted to each other. But now this sulfate, right, is so much more attracted to this hydrogen. It's going to hold on to it even tighter, which means that whatever kind of ionization occurred here, when this ionizes or comes apart, it's going to be even less, right? Which means that it will be a weaker acid. Now, what do I mean by that? So when this comes apart, let's just practice your quiz this week. If this is an acid, then this is a base. Acids lose, bases gain. So this first equation here made more H3O plus than the second equation, right? Because this is like, no, you are not taking my hydrogens, no, right? And so the more acid, the more hydrogens you remove, the weaker the acid is. So every time we ionize a hydrogen, the weaker it is. And we're going to actually look at those Kas in just a second. Now, how do we figure out how much of it ionized? We use percent ionization, but we've been doing this the entire time. This is that X is small approximation. When we test if X is small works, what we're doing is we're seeing the percent of the original reactant ionized, right? So this percent ionization is literally our X is small. This is our X is small, right? This is our X over our original. This is that top left box on your ice table, right? So a nice question that you're going to get next week is, what's the percent ionization? You only have to do half a ice table to do this, right? You only have to do a little bit. So again, this percent ionization, this is just going to be, when you actually find the percent ionization, it'll just be weak acids that we're doing this with, because strong acids ionize 100%. Okay, so now HNO2. Let's practice this week's quiz. When you put it in water, we said this is an acid. Therefore, this is that's supposed to be a B. This is a base. Acids lose. Conjugate base. Bases gain. Conjugate acid, right? This is your quiz this week. Very important that we do this because in order to do our ice table, we have to know what we're putting in it, right? So for our ice table here, said we started with 2.5. Remember, it has to go to our products because we only have reactants. So this is going to be, right, minus x plus x plus x. It's got to go forwards. It's going to go down by 2.5 minus x. Our Ka has to be given to us for this problem. Let's just assume x is small. Now, will x is small work? Yeah. Now, how do I know x is small work? This is a -4, and that's a 1. It'll work. But our x is small, remember, is our percent ionization, right? So they are the same thing. So when we solve for x, remember we're assuming this is small, we get 3.4 times 10 to the -2. Now, at this step in a normal ice table, this is when we would do the x is small. But again, x is small is the same thing as finding the percent ionization. What we're going to do is we're going to see, is this change? So this is the change, right? What is that change? X is small, we just look for, oh, is it less than 5%, right? Percent ionization just says whatever it is, it is. So when we do this, don't worry about this piece. 1.4%, right? And I could see that it was going to be less than 5%, again, because our Ka was 10 to the -4 and this was 1. So it was definitely going to work. This is the same thing again as that x is small assumption that we do, right? It's the same thing. So saying our x is small is valid is also our percent ionization. So we love percent ionization questions because percent ionization questions is the same thing we've been doing. Okay, so let's try one more of these. I want to know the percent ionization for this problem. Let me give you the Ka. There you go. All right, try the percent ionization for this problem. Again, all you're doing is getting to that x is small part in your ice table, right? That's as far as we're going on this. Okay, try this and then we'll go over it in just a minute. Okay, I got a bunch of these and they're all looking correct. So very nice on this one. Okay, so here's the reaction, right? We set up our ice table, set up our X's, which are very consistent to what we've been doing. We're going to assume X is small, right? That's our next step, right? Then solve our math. Oops, let me leave this math here just in case anybody needs it. We use our Ka, right? So 1.4 times 10 to the negative 5 equals x squared over 1.2 times 10 to the negative 2. The square root of that, right? When we do that, our x equals 4.1 times 10 to the negative 4. Right, so now that's our x. That's this x. So now we take this over our original concentration, just like we would do x is small. But again, it's also percent ionization, right? It's the same thing. So when we do that, our x over original, we get 3.4%. Now, I knew this one was going to work because our k was so small, and actually this one I didn't know was going to work. It would have been on the border. It would have been pretty close because this is -2. So one of the question was, is it always less than 5%? Nope, not necessarily. Remember, when our x is small didn't work on one we did like 3 of them ago, we got 33%. So no, x is small doesn't always work. It's just the x is small process that we use when we check it, that is the percent ionization. So it's like we're killing 2 birds with 1 stone. So x is small is both of those. It's percent ionization and our x is small assumption. Okay. Now, when we do our H3O plus and our HA, remember, this is our percent ionization. It's, again, the same thing as our x is small. That's the same thing we've been doing. So when you increase the initial concentration of acid, it results in an increase of H3O plus at equilibrium. If you increase the concentration, if you increase the initial concentration of the acid, actually results in a decrease in our percent ionization. So let's look at this in general. HA plus water. Again, here's this week's quiz. Acid, base, acids lose, bases gain, right? So this would be conjugate base, conjugate acid. Again, this week's quiz. This is just a Le Chatelier's question here, right? So if you increase the concentration of acid, I'm going to take this over. Think Le Chatelier's. If you increase the concentration of your acid, right, it results in an increase amount of H3O plus, right? Just Le Chatelier's principle. So, which means that we don't have time to talk about this. Oh, 5 minutes. We're just going to go. We'll just do this quickly. Okay. And we'll talk more about this one. Okay, so when we have that ionization of our weak acid, so here's our weak acid. According to Chatelier's, if you reduce the concentration of all of these, equilibrium should shift to the right, right? So ignore water. If you decrease the concentration, so you make them all dilute, right? Then it should shift towards the right, because what it's going to try to do is going to try and keep the same number of particles, just like when we talked about Le Chatelier's. But if you do this, then we'll end up with a larger H3O plus in the dilute solution compared to the initial solution, which will actually give us a larger percent ionization, right? So now, what does this mean? So if we have two acids, so let's say we have a mixture of acids. So let's say we have a strong acid and a weak acid, right? So the strong acid, so let's say we have got our weak acid right here. This is our weak acid. And I'm going to add strong acid to this reaction. I'm going to put in a ton of this, right? Because remember, strong acids 100% dissociate, which means we're going to dump in a bunch of H3O plus. We're just pouring H3O plus in. According to Le Chatelier's, it's going to shift the equilibrium of that weak acid over to the left, right? Which means it's going to decrease the ionization of that weak acid. So when we have mixtures of acids, a weak acid and a strong acid, because the strong acid makes it shift over to the left because of Le Chatelier's principle, we can actually ignore the contribution of that weak acid. So, okay. Just to summarize what we talked about. So in general, if you have a strong acid and a weak acid, the strong acid, again, shifts that weak acid so far to the left that the contribution to the H3O, the contribution of the weak acids H3O plus is negligible. It just doesn't even matter, right? Because it's so tiny. So if you have two acids and one is much stronger than the other, you can ignore the weaker one. This goes for weak acids too, right? If you have, for example, I'm just gonna show you this one problem. Here are two acids, right? These are two acids. Look at how much stronger this one is, 1,000 times stronger, right? Both of these are weak, right? These are both weak acids, but this weak acid is 1,000 times stronger than this acid. Because of that, the contribution to this H3O plus, when you add it, is going to shift this one over here, making this one completely negligible. So when we do our ice tables, we ignore it. Like we pretend it's not even there. This is the question now, right? The question is literally just HF. We literally will do the problem ignoring that HF was there. I mean, that HClO was there because it's so much stronger, right? So we're going to end there today, but I wanted to get to this piece. For those of you who are on this homework, if you have a mixture of acids or a mixture of bases, and one is much stronger than the other, you can just ignore the weaker one and you continue the problem on just as the strong one.